Hello students, in this lecture we will be solving few numerical problems related to first order system, the one which we have already discussed in the previous lectures. So let us take the first numerical problem. Now the first numerical problem is a mercury thermometer is having a time constant of 0.1 minute, is placed in a temperature bath of 100 degrees Celsius and is allowed to come to equilibrium with the bath. Okay. At time t equal to 0, the bath temperature begins to vary sinusoidally about its average temperature of 100 degrees Celsius with an amplitude of 2 degrees Celsius. Alright. If the frequency of the oscillations is 10 by pi cycles per minute, plot the ultimate response of the thermometer reading as a function of time. What is the phase lag? Okay. Now the question is related to the mercury thermometer. So let's find out the solution to this query. Solution. Now we know it's a mercury thermometer. So mercury thermometer is having a transfer function ys upon xs as 1 upon tau s plus 1. We know that. Now time constant is given, so tau value is given, which is 0.1 minute. Okay. Further, the steady state value is given. Initially steady state is given, so that is surrounding temperature is same as the thermometer reading, which is 100 degrees Celsius, right. Now at time t equal to 0, the bath temperature varies sinusoidally, so that means now x t, that is the surrounding temperature, which is I am taking the deviation variable capital Xt, which is a sin omega t, where a is represented as 2 because the amplitude is written as 2, and omega t will find that out. So xt is 2 sin omega t, that is given. Further, if you notice that there is a frequency is given, that is 10 by pi cycles per minute. Now omega will be equal to 2 pi f. So 2 pi f into 10 by pi, which comes out to be 20, that is radians per minute. So omega is given 20 radians per minute, so x becomes 2 sin 20 t, right. Now for this input, what will be xs? Xs we know, for a sin omega t it's omega upon s square plus omega square, right. And obviously if it is a sin omega t, so we'll have a over here, x. Now for this x, if we substitute over here, we have y. Now we already familiar with the first order systems with the sinusoidal function. Now yt is, we can derive, that is a under root of tau square omega square plus 1 into sine of omega t plus phi. That we are familiar with, which you have derived in the lectures. So now we know that, we know the value of a, we know tau, we know omega, and we know phi. Now phi is tan inverse minus tau omega. So we know all the values of a, tau, omega, and tau. We can substitute over here and we can have your yt. Now yt comes out to be, after substituting the values, yt comes out to be 0.894 into sine 20t minus 63.43 degrees Celsius. Now let's see how to get this omega frequency. Now phi was tan inverse minus tau omega. Tau is 0.1 and omega is 20, so tau omega is 2, so phi is tan inverse minus 2, which comes out to be basically minus 63.43 degrees. Clear? So we have the answer over here, that is yt is this much. Clear? Now yt is this much. So now so now we have, we determine the yt. Now let's try to plot it. Okay, now we're gonna plot yt over here. Now let me write again yt over here. Now yt is 0.894 sine of 20t minus 63.43 degrees, right? What will be yt, because this was capital YT, so what will be small yt? Small yt will be ys plus this term. So what was ys? That is 100 plus 0.894 into sine of 20t minus 63.43. This is your thermometer reading. What will be the bath temperature? Bath temperature will be, we know that x minus, okay, x minus capital X t. Capital X t was, what was capital X t? Capital X t was 2 sine 20t. Clear? So it is 2 sine 20t. So from here what will be small x t? Small x t will be nothing but 100 plus 2 sine 20t. So now with the different values of t, we'll have different values of xt and we will have different values of yt. Clear? So we can put different values of t and we can have different values of xt and yt. Now let's plot. Let's say okay, now this I've done it wrong. Let me put it somewhere in the middle, because we know it's a sinusoidal. So let's say this is time and we have response on the y-axis. Now if we know this is your xt, which is having maximum value of 102 and minimum value of 98, because you know 100 if plus 2 or minus 2, because it's actually basically, you know, moving sinusoidally between these two values, so the average comes out to be 100. Now the response, that is yt will be, if you're going to plot this term for different values of t, you will have the response by this green line. Clear? That is, the amplitude is somewhat less than the input amplitude, plus there is a lag. Now we need to calculate this lag, because it says over here what is the phase lag. Now we know that it's 63.4 degrees, phi. Now phi we have calculated over here. Now let's try to calculate your phase angle. Now for phase angle, we know that frequency is 10 by pi cycles per minute. What do you mean by this? That means in 10 cycles, 10 by pi cycles occurs in 1 minute, right? So one cycle will occur in how many minutes? Pi by 10 minutes. Now one cycle means 360 degrees in pi by 10 minutes. How much will be 63.43 degree will take place? So that will be 10 by pi into 63.43 divided by 360 degrees, which comes out to be 0.0553 minutes, which is roughly approximately equal to 3 seconds. That means the output lags the input by 3 seconds, and that is determined by this thing. Clear? So this is how you determine. That means output lags the input by 3 seconds. Clear? So this was the question. Moving further to the next question. And the next question is, we have a process of unknown transfer which is subjected to an unit impulse. Okay, the output of the process is measured accurately and it's found to be represented by a function yt, which is t e minus t. Determine the unit step response of this process. Okay, now in this question, we do not know our transfer function. Clear? Because it says it's unknown, but this transfer function is given a unit step impulse. That means xt is given as delta t. So what will be xs? Xs is 1. So that is still output is unknown. Clear? But it says the output yt is given. That is yt is given when the Laplace of this term is Laplace inverse of this is taken, it comes out to be te minus t. So if yt is given, we can calculate ys from here. What will be ys? Now for t, it's 1 over s square, and if it is having e minus t, it becomes you s plus 1 raised to power square. Now ys is known, xs is known, so our transfer function is basically ys upon xs, which is 1 upon s plus 1 whole square. Clear? Now we know our transfer function. Now this is our transfer function. Now we need to determine the unit response of this process. That means xt is now ut, unit response, unit step. That means if the input is unit step, what will be xs? Xs is 1 upon s. So what will be ys? Ys will be s into s plus 1 whole square. Clear? Now we can do the partial fractions of this term, s over s plus 1 whole square, which can be written as a over s plus b over s plus 1 plus we have c over s plus 1 whole square. By solving this, we can get the values of a, b and c. Okay, I've solved it. Now a comes out to be 1, b comes out to be minus 1, and c comes out to be again minus 1. So substituting the values of a, b, c in this equation, that's over here. So we have 1 over s minus 1 over s plus 1 minus 1 over s plus 1 whole square, and this is your ys. So now we can take the Laplace inverse. So yt comes out to be Laplace inverse of 1 by s. It's 1 over s plus 1 minus e minus t, and this becomes again te minus t. So this becomes the Laplace of this question, Laplace inverse of y. That's the response. Clear? So this is how you solve your problems. Second, moving further. Okay, now this is a good question. Now read the question very carefully, because once you are familiar, once you understand the question, then it's very easy to solve. If you are not able to understand the question, then it's become quite difficult to solve. Okay, now the question says a tank is having a time constant of 1 minute. Okay, now let's write down the solution over here. Now time constant is given 1 minute. Okay, and a resistance is given, which is 1 by 9. Okay, is operated at steady state with inlet flow rate of 10 feet cube, right? So that means in a tank there is an inlet, there is an outlet, there is a resistance over here. Okay, now this Q is given as 10 feet cube per minute, right? At time t equal to 0, the flow is suddenly increased to 100 feet cube for 0.1 minute. Okay, by adding additional 9 feet cube of water in a tank over a uniform period of 0.1 minute. That means now additional water is being added into the system. Additional water is added, that is 9 feet cube per minute over a period of 0.1 minute. Now we need to plot the response and compare with the impulse. Now for impulse, it says the input approaches an impulse function having a magnitude of 9. Okay, no problem. Now let's first try to solve the part A of the solution. Now part A says, now let's try to first analyze the system. We know that, okay, no doubt, for it's a simple liquid level tank, so we know the transfer function is nothing but r over tau s plus 1, where r is 1 by 9, and what is tau? Tau is a into r. Area of the tank is given. How much area is the area of the tank? Okay, now tau we don't, area is not known, so we know the value of tau. Tau is given, that is 1 minute. So it's, so this is the transfer function of the tank. But now we need to find out xt first. Now xt has been defined in this thing that additional 9 feet cube is added over a period of 0.1 minute. So now let's try to find out your xt. Initially at time t equal to 0, what was the input? The input of 10 feet cube per minute. At time t equal to 0, 9 feet cube of water, at time t equal to 0 the flow increased to 100 feet cube, okay, right? Now at time t equal to 0 the flow reaches to 100 feet cube per minute, right? By adding additional 9 feet cube over a uniform period of 0.1 minute, that means till t equal to 0.1 minute this flow remains at 100 degrees Celsius, and then after 0.1 minute it again comes back to its initial, because it says over here that flow is suddenly increased to this for 0.1 minute. That is, for 0.1 minute the inlet becomes 100 feet cube, and thereafter it again comes back to its initial state. Now what is this type of response? This is basically the example of your pulse input. Now for pulse input, so what will be your xt? Now what will be the xt? Xt is basically you have ut and you have again u t minus 0.1 minute. And how much is the magnitude? 100 minus 10, 90. So that is your xt. So xt becomes, so xt is basically nothing but 90 of ut minus u t minus 0.1. So we can have your xs. What will be xs? 90, ut is 1 by s. This becomes, now this is again ut, that is 1 by s, but there is a lag of 0.1 minute. So we're gonna write over here e minus 0.1 minute. So this is nothing but 90 upon s into 1 minus e minus 0.1 s. So that is your xs. Now we know what is your our ys upon xs. Our ys upon xs is 1 by 9 of s plus 1. We know xs, put this value over here, so we have your ys. Now ys comes out to be 90 by 9 into 1 by s into s plus 1 of 1 minus e minus 0.1 s. Now how to solve this thing? Now this becomes, if let's simplify, this becomes 10 over s into s plus 1 into 1 minus e minus 0.1 s. It can be written like this. Now let's try to solve. Okay, this can be written as 10 over s plus 1 minus 10 over s into s plus 1 e minus 0.1 s. Now in order to solve such questions, it's a very simple thing. Let's try to find out the Laplace inverse of this term. Once we find out the Laplace inverse of this, then the Laplace inverse of this can easily be written. Clear? Because if you see, this term is common in both, so we can find out the Laplace inverse of this, and then we can write down this term, and then we can club both the solutions. Now Laplace inverse of this, that is 10 over s into s plus 1. It's very simple, a over s plus b over s plus 1, and solve it. We can have the values of a and b. A comes out to be 1, b comes out to be minus 1, so this becomes 1 over s minus 1 over s plus 1. So if you take the Laplace inverse, this becomes 1, this becomes e minus t. Clear? So that means the Laplace inverse of this is 1 minus e minus t. That is 1 minus e minus t. Clear? So if we see this term, now for first half, that is for this thing, we have already solved the solution, we already know the solution. Clear? For the second part, that is for this part, again 10 over s plus 1, that term is there, so we can again write the same term, 1 minus e minus t. Clear? But now over there we have an exponential of minus 0.1 s. Now wherever this term is occurring, now what we gonna do, simply wherever t is written, we gonna add minus 0.1 in that time term, add minus 0.1 in that time term. So this is your final solution, that is yt. Now again you see over here, now this was your yt, this was your ys, sorry, this was your ys. Now we need to take the Laplace inverse of this to calculate yt. Now yt can be calculated in a simple way. First we need to find out the Laplace inverse of this term that we have already calculated, that is 1 minus e minus t, that is written over here. Now again for this term, 10 over s into s plus 1, that is already repeated, so we can write the same term again, but wherever now this t is occurring, over there we can write, we can subtract 0.1 from that t, so this becomes this term. Now this solution is valid, now this solution is valid into two categories. One is your yt is 1 minus e minus t, subject to condition that your t is less than 0.1, that you see over here. If you see over here in this part, if the time is less than 0.1, that means it's increasing, it's increasing, so it is this thing, and it becomes this complete solution, that is 1 minus e minus t minus 1 plus e minus t minus 0.1, that is for t greater than 0.1, or this can be further simplified. Now this minus 1 gets cancelled up, and we have minus e minus t plus e minus t into e 0.1, which can be written as 1.052 e minus t. Clear? So this is valid for t greater than 0.1. Now let's try to plot this thing. Time, and we have response, that is yt. Now initially when time is 0.1, less than 0.1, it is following this thing, that means it is increasing. Clear? Now when the time reaches, this is t equal to 0.1. Clear? And when the time is greater than 0.1, it is following this graph, so it will follow this thing. Clear? So this is your yt for t greater than 0.1, and this was for your yt for t less than 0.1. Now we need to compare this response with that of the impulse. Now for impulse, we have ys upon xs as this term. Let me write over here. Now ys upon xs is 1 by 9 of s plus 1. Now impulse is 9 delta t of magnitude 9, it's given in the question over here, impulse of magnitude 9. Okay, now it is this thing. Now what will be xs? Xs is 9, so put this value over here. So what is ys? Ys is 1 upon s plus 1, and what will be yt? It is nothing but e minus t. So if you see, for the pulse function, yt was 1.052 e minus t, and for impulse function yt is e minus t. It's almost similar. So for impulse function, the plot will be something like this. So this is impulse. Now this, and in this question you can clearly see how much is this time period. This time period was hardly 6 seconds. If you decrease this 6 seconds it towards 0, it becomes a problem of a impulse function. So this was your impulse function, this is pulse function, and if you compare the results are almost comes out to be the similar. Clear? So the only difference is in the pulse function we're gonna have two types of solution. One is for less than 6 seconds, that is this part, and one is for t greater than 6 seconds, that is this for initially it will follow this profile and afterwards it will follow this profile. Clear? So this is how you solve such problems related to your pulse system. Moving further, okay, the third question, it's a very good question. A tank is having a cross-sectional area 2 feet cube and a linear resistance of 1 feet per centimeter cube per minute, is operating at steady state flow rate of 1 centimeter cube, 1 cubic meter at time equal to 0. The flow is given by this profile. Determine Qt and Qs by combining the simple functions. Know that Q is the deviation in the flow rate. Okay, obtain the expression of Ht. Okay, now it's very simple. Now the solution of this, we know that it's a tank. So for tank, what is Hs upon Qs? It's R upon tau s plus 1, where tau is AR. Now area is given, resistance is given, so we can substitute that value. So what we have is 1 over 2s plus 1. Clear? Now we need to find out Qs. Now Q is following this profile. Now what will be Qt over here? What will be Qt? Now initially at time t equal to 0 it was 1. Clear? At time t equal to 0 it was 1. For t greater than 0 it becomes variation with time. So what is this profile? This profile is your ramp function. So it is t ut with the magnitude of 1 and it continues till 1. At time t equal to 1 the ramp is stopped, so it becomes t minus 1 u t minus 1 and it remains there and the flow rate continues to follow. So this is your Qt which you have determined from this plot. Now what will be Qs? If you take the Laplace of this tut ramp function, it is 1 by s square minus tut again 1 by s square, but now we'll have a lag of 1 second, so it is this thing. So it becomes 1 minus e minus s by s square. So we have Qs. We can substitute this Qs over here and calculate our Ht. So let's find out Ht. Okay, now Hs by Qs is 1 over 2s plus 1 and Qs is 1 minus e minus s by s square. So Hs becomes 1 over es plus square into 2s plus 1. So again it can be solved. First let's try to solve for 2s plus 1 and then we can write it for the second term, that is 2s plus 1, that is for this part. Now let's try to solve this thing and this can be written later on. So 1 over s square plus 2s. Now this can be solved. 1 over s square into 2s plus 1, it can be written okay, or let me write it in the other way. Can I write it as 1 over s square into s plus half into half. I've taken 2 outside, so this can be written as a over s plus b over s square plus c over s plus half. Then you can find out the values of A, B and C. Clear? Now A, B and C comes out, if you solve for A, B, C and C, A comes out to be minus 2, B comes out to be 1 and C comes out to be 4. So upon substituting for the values of A, B and C, this becomes minus 2 by S, 1 by S square plus 4 over S plus 1 by 2. Now taking the Laplace of this becomes minus 2 ut, this becomes 1 by S, so tut, and this becomes 4e minus t by 2. Clear? So that means the Laplace of this, Laplace inverse of this, is this term. So finally your ht will be first for this term, that is minus 2 ut, which we have solved over here, for e minus t minus 2, that is this part. And for the second part, again it's the same terms will gonna come over here, with the addition that wherever t is written, we're gonna have t, we're gonna replace t by t minus 1. So it becomes minus 2 u t minus 1 plus t minus 1 u t minus 1 plus 4 e minus t minus 1 by 2. So that is your final solution, that is ht. Clear? So this is how you're going to solve it for either pulse systems or the systems which are having a delay. It's very simple. First try to solve it for the system which is having non-exponential terms. You're going to have that their response, and for the other term simply replace t by the term t minus 1, that is the lag term. Clear? Next question. Now in the next question, it's a very easy question. We need to determine y at t equal to 5, where ys is given as this thing. Now again it's the same term, e minus 3s over s into 7s plus 1. Again, the only method to solve this thing is first try to find out the response of s over 7s plus 1, or it can be written as 1 by 7 over s into s plus 1 by 7. Let's try to find out the Laplace inverse of this. So this can be written as a over s plus b over s plus 1 by s. So solving this thing, you can calculate the value of a and b. A comes out to be 1, b comes out to be minus 1. Clear? A is 1, b is minus 1, so it can be written as 1 over s minus 1 over s plus 1 by 7. If you take the Laplace inverse, this becomes 1 minus e minus t by 7. Clear? So this is what the response is for this term, but now we have e minus t, e minus 3s, so simply replace your t by t minus 3. So your yt will be nothing but 1 minus e minus t minus 3 by 7. So that's your response, that is yt. Clear? Now that's the answer for your response yt, but now we need to determine y at t equal to 5. So put t equal to 5, so what will be yt? That will be 1 minus e minus 5 minus 3 by 7. Solve it and you will have your yt at t equal to 5 as 0.0248. Clear? That's the solution. So this is how you solve your numerical problems. Now you can refer to more problems related to first order systems from your book Kafner. Thank you.